In this lecture, I would like to discuss about the distribution of electrons in metal d orbitals when the splitting of the d orbital is takes place. In previous lecture, we discussed about crystal field splitting in octahedral complexes. So you can see in this diagram, the 5d orbitals are splitted in the two groups, the higher energy level Eg orbitals and lower energy level T2g orbitals. There is a rise in the energy level of Eg orbitals, that is doubly degenerate orbitals, and decrease in the energy level of T2g orbitals, that is triply degenerate orbitals. So the 5d orbitals are splitted. These 5d orbitals are splitted into the two groups. Therefore, how we can distribute the metal d electrons in these T2g orbitals and Eg orbitals? This is happen because of due to the crystal field splitting in octahedral complexes. As the metal d orbitals are splitted into the two groups due to the surrounding ligand field. Lower energy group, it is T2g orbital, and higher energy group, it is Eg orbital. Now how we can distribute the electrons of the d orbitals of the metal into T2g orbitals and Eg orbitals? So let us see this. So distribution of electrons in metal d orbitals in weak and strong ligand fields. Distribution of metal d orbitals in weak and strong ligand fields in presence of weak ligand and in presence of strong ligand. How we can distribute the metal d electrons? Now we know that in octahedral complexes, as the d orbitals are splitted into the two groups, the distribution of electrons in the d orbitals is based on certain rules. The distribution of electrons in the d orbitals, it is based on the following rules here. The first rule is that electrons prefer to occupy the lower energy orbitals. First of all, the electrons will be entered into the lower energy orbitals than in the higher energy orbitals. Second rule is that electrons obey the Hund's rule. That is, electron pairing will not take place until all the available orbitals of the given set have one electron each. The electron pairing will be takes place only when the each orbital should be occupied by the single electron. So according to the Hund's rule of maximum multiplicity, each orbital should be occupied the electron, unpaired electron, and electron pairing will not take place until all the available orbitals of the given orbital having one electron each. For example, there are 3p orbitals. There are 3p orbitals. So suppose that for p4 arrangement, suppose there are 4 electrons, then we can distribute 4 electrons in this way. Each orbital should be occupied by the single unpaired electron, then pairing will be started. Not as like of this. We cannot place the 4 electrons in this way. So this is wrong. Each orbital should be occupied by the single electron and then the pairing will be started. This is the second rule. These two rules are already known to us. Now the third rule is important here. If the energy to place an electron in the higher Eg level is greater than the pairing energy, if the energy to place an electron in the higher energy Eg level is greater than the pairing energy, then the electrons are paired up into the T2G orbital. The electrons are paired up into the T2G orbital. Once again, I would like to repeat this rule. If the energy to place an electron in the higher energy level is greater, it means that we want to place the electron into the EG orbital, but it is higher than the pairing energy. Then the electrons are preferred to paired up into the lower T2G orbitals. So this situation arises only when, let us show this. This rule, this situation arises only when, if the energy required to place the electron in the EG orbital is greater. Let us show this. The splitting of the 5D orbitals. The 5D orbitals are splitted into the two groups. That is higher energy orbital and lower energy orbital. Higher energy orbital, it is EG orbital, and lower energy orbital, it is T2G orbital. Now there are two EG orbitals, that is dz square and dx square minus y square, and three T2G orbitals, dxy, dyz and dxy. And there is an energy gap between the EG orbital and T2G orbital. Now this energy gap, it is called as delta O, or it is also called as 10 dq. Now what does third rule says? According to the third rule, if the energy required to place the electron in the EG orbital is greater than the pairing energy, that is 10 dq is greater than the pairing energy, 10 dq is greater than the pairing energy, then the electrons are paired up into the lower T2G orbital. It means that if this energy gap is larger, or if the energy required to place the electron into the EG orbital is greater, then electrons are preferred to paired up into the lower T2G orbitals. Okay. Electrons are preferred to paired up into the lower T2G orbitals. This is the third rule. Now the fourth rule. If the energy required to place the electron in the EG orbital is less, that is 10 dq, it is less than pairing energy. 10 dq, it is less than pairing energy. It means this energy gap is less. The energy gap between the T2G orbital and EG orbital, it will be less. So in this situation, the electrons will be entered into the EG orbital. Okay, you can see here. If this energy gap between the T2G orbital and EG orbital, it will be less. That is 10 dq. It is less than pairing energy. It means this energy gap will be less. Then the electron can be entered into the EG orbitals. So these four rules are very, very important here. How to distribute the metal d orbitals, metal d electrons into the T2G orbital and EG orbitals. So once again, let us see the third rule. If the energy to place an electron in the higher EG level is greater than the pairing energy, then the electrons will be paired up into the lower T2G orbitals. And fourth rule is that if the energy to place an electron in the higher EG level is less than the pairing energy, in the lower T2G orbital, that is when 10 dq is less than pairing energy, then the electrons will be entered, or electrons will occupy the EG orbitals. Okay. Now, the distribution of electrons in the metal d orbitals will depend upon the surrounding ligand field. Where the ligand field is strong or the ligand field is weak. In presence of the strong ligand field, if the strong ligands are coordinated or bonded to the metal, then the splitting of the d orbitals will be greater. The splitting of the d orbitals will be greater. And if the weak ligands are bonded to the metal, then the splitting of the d orbital will be less. So therefore we can say that ligands which produce the weak field cause splitting of d orbitals to a lesser extent. It means that ligands do the less crystal field splitting of the d orbitals. And generally such ligands are called as weak field ligands. So what is the example of the weak field ligands? Fluoride, hydroxo, chloro, bromo. Such ligands are produces weak field around the central metal ion. And hence the degree of the crystal field splitting will be less. The d orbitals are not splitted too much. That is, the energy gap between the Eg orbital and T2G orbital will be less in presence of the weak ligand field. Or we can say that 10 dq is less than the pairing energy, or the energy gap between the T2G orbital and Eg orbital will be less in presence of the weak ligand. On the other hand, ligands which produce strong field split the d orbitals to a larger extent in presence of the strong ligand, or in presence of the strong ligand field. The crystal field splitting will be larger. That is, the energy gap between the T2G orbital and Eg orbital will be larger. Such ligands are called as strong field ligands. For example, cyano, carbon monoxide, these ligands are strong ligands. When such ligands are bonded to the metal, they will provide a strong ligand field to the central metal ion. And in presence of the strong ligand field, the degree of the crystal field splitting will be larger. Hence, the metal d orbitals are splitted to the larger extent. That is, the energy gap between the T2G orbital and Eg orbital is large. So we can say that 10 dq is greater than pairing energy. So the value of the 10 dq will be larger in presence of the strong ligand field. Now the crystal field splitting ability of the ligands decreases in the following order. It is decreases in this order. It means that carbonyl, carbon monoxide, cyano, nitro, ethylene diamine, ammonia molecules. Such ligands are the strong ligands. They are called as a strong ligands because they provide a strong ligand field. Now water molecule, fluoro, hydroxo, these ligands are called as a weak ligands. So in presence of the weak ligand, the crystal field splitting is less. And in presence of the strong ligand, the crystal field splitting is greater. So in this way, ligand field strength will affect onto the crystal field splitting. So in a weak field ligand, 10 dq is usually less. In presence of the weak ligand field, the value of the 10 dq is less, okay, than pairing energy. That is 10 dq is less than pairing energy. This 10 dq, it is less than pairing energy. Hence, electrons remain unpaired and form high spin complexes. The complexes which are formed are called as high spin complexes. For example, now see, for D4 configuration, where 4 electrons are there in the d orbitals. So we know the splitting of the d orbitals. There are 4 electrons into the d orbitals. So we can distribute these 4 electrons. 1, 2, 3, 4. We have to distribute the 4 electrons here in the T2g orbitals and into the Eg orbitals. Okay. Now, in the T2g orbitals, lower energy orbital T2g and higher energy orbital Eg. So as this energy gap will be smaller, 10 dq value will be less than the pairing energy. So first 3 electrons will be entered into the lower T2g orbitals according to the Hund's rule. Each orbital should be occupied by the single unpaired electron. Then the 4th electron will be entered into the Eg orbital because this energy gap will be less. In presence of the weak ligand field, 10 dq is less. Hence the electrons remain unpaired. All the electrons are unpaired here. And such a complex is called as a high spin complex. So particularly in presence of the weak field ligand, as there is a smaller energy gap between the T2g orbital and Eg orbital, the pairing of the electron is not takes place. When all the orbitals are occupied by the single unpaired electron, then the pairing will be takes place. Okay. So what is a high spin complex? Complexes in which electrons remain unpaired to the maximum possible extent. Maximum number of the unpaired electrons should be there. Such complexes are called as high spin complexes. So in presence of the weak ligand field, which complexes are formed? High spin complexes. Because this 10 dq, it is less than pairing energy. And this energy gap is less. So electrons remains unpaired here. But now in the case of the strong field ligand, 10 dq is more than pairing energy. This energy gap, let us show this. The energy gap between the T2g orbital and Eg orbital, it will be higher here. Okay. This is supposed to be T2g orbital. It is Eg orbital. And now this energy gap, it will be higher. This energy gap, it will be higher. So for D4 configuration, as this energy gap will be higher, first 3 electrons are entered into the T2g orbital. First 3 electrons will be entered into the T2g orbitals. And as this energy gap will be higher, the 4th electron get paired up into the lower T2g orbitals because the ligand field will be strong. So in presence of the strong ligand field, 10 dq is more than the pairing energy. This 10 dq, it is more than pairing energy. This energy gap will be greater. So the electrons can be paired up into the lower T2g orbitals. Hence the electrons paired up in the lower energy orbitals, and it will form a low spin complex. What is a low spin complex? Complexes in which electrons pair up to the maximum possible extent, leaving minimum number of unpaired electrons. So in case of the low spin complex, number of the unpaired electrons are very, very less. Mostly the electrons are paired. So in presence of the strong ligand field, as 10 dq is more than pairing energy, hence the complexes which are formed are called as the low spin complexes. So thus we know that in presence of the weak ligand field, the crystal field splitting will be less. The energy gap between the T2g orbital and Eg orbital will be less. So electrons remain unpaired, and such complexes are called as high spin complexes in presence of the weak ligand field. But in case of the strong ligand field, 10 dq is more than the pairing energy. Hence electrons paired up into the lower T2g orbitals. Electrons paired up into the lower T2g orbitals. So in this way, we have to distribute the electrons into the metal d orbitals by understanding the rules. The first 2 rules are very common. Electrons are preferred to occupy the orbitals of the lower energy level. Of course, the electrons will be entered into the lower energy level. Then electrons obey the Hund's rule. Each orbital should be occupied by the single unpaired electron. Then the pairing will be started. These two rules are the common rules. Then third rule is that it is very important. If the energy to place an electron in the EG orbital is higher than the pairing energy, then the electrons are paired up into the lower T2G orbital, that is 10 dq is greater than pairing energy. And fourth rule is that if the energy to place an electron in the higher EG level is less than the pairing energy, then the electrons will be entered into the EG orbitals. So these are the rules belongs to the distribution of the electrons in the metal d orbitals.